Hey, good afternoon. So, so some of you have met me over the weekend for the project. I wanted to spend a few minutes going over some of the project ideas that I suggested when we met. For those of you who are still to meet me. Also, this is the same slide set, which the pointer to which is on Piazza, so you can look at these additional slides. So a few listed out here, and then there are a few more slides with more detailed project ideas. So I think one interesting project, so firstly, to step back, I want to avoid projects where you simply take some data, even if it's sensory data set, and just propose to make some sort of an inference out of it. And the reason being that there's nothing distinctive in that particular case about the nature of the problem. Almost, if you've done any course, you've probably gone through the cycle of taking a labeled data set and training a model and evaluating it. So I want to stay away from those kind of projects, and rather you should use your project to explore some dimension which makes kind of the problem non-straightforward. Just so here are some which came up in the discussion. So one is this whole notion of imputing sensor data. I had listed it originally also, but just want to talk a little bit more about it. So imagine you have some data set, either temporal or spatial or spatio-temporal. So by that I mean some time series data, some data collected, sensor data collected from distributed sensors, or some combination. And imputation refers to if you have some data missing, then how do you fill it in? And intuitively, imputation can be done by making use of history, or if you are imputing something in the past, kind of like smoothing that we discussed, then it's looking at history and future. So a little bit of context, both before and after. And you can think of the same thing in terms of space. Intuitively, nearby things or things which share similar features have higher correlation. So one can make use of similarities of where a sensor was. So the project exploration out here would be there are many schemes for imputation that people have proposed, both for space and time. So one direction could be to compare them. The other is really look at how well they do. So intuitively, if the gap missingness is huge, then you will have a hard time filling it in. On the flip side, if your phenomenon is very predictive, like let's say a sine wave or something, then filling is easy. So what this says is that if the process has structure, it's easier to impute. If missingness is long, then it's harder to impute. If you have more context, then perhaps it's easier to impute because you can learn the structure more easily. Sometimes you impute also laterally by making use of other sensors. So an example that I cited to the group which met me was that if you look at inertial sensors, which are in your phone, they have 9 degrees of freedom. You have 3 accelerometer, 3 gyroscope, and 3 degrees of freedom of magnetic field. And yet rigid body only has 6 degrees of freedom. So there are clearly 3 extra degrees of freedom. And there are, if you Google, you'll find papers like virtual gyroscope, which basically says that purely from a physics equation perspective, you can compute angular velocity given acceleration, linear acceleration, and the direction from the Earth's magnetic field. The problem is we still have gyroscopes because doing it computationally is very noisy. But clearly there is redundancy out there. Other cases, like another example I gave was, let's say you're watching a video and sound drops out, but by watching the lips, you can still make out what the person was saying. So clearly, these are all examples where we are able to fill things in by making use of other sensory data. So the goal of this project would be to see how effective these different schemes are. Some of them maybe work for small losses, some can work for big. So that would be one direction. Another related thing, and perhaps part of the same project, depending on your team size, would be to see, should we even impute? And the kind of the argument here is the following. If I have some missing data and I repair it by imputing, I'm not adding any new information to it, right? I mean, after filling it in, the new time series literally has the same information that it had before. There's nothing new that you added to it. So if I'm not adding any new information, then if I have a task to do, whether I do that task on the original time series where there were dropouts, and whether I do it on time series which has been repaired, I should be able to do the same thing. And yet we impute. And so the question is, why do we impute? Well, one reason is oftentimes our downstream software is designed, it expects kind of a clean time series. So you can think of imputation as part of a cleaning up process. Sometimes it's because our algorithms are implemented so that if things are very regular, then they run faster, okay, as opposed to if I have to deal with this missingness. So it could be performance, could be software engineering, but there are schemes which work directly on time series or spatial data where you don't assume any regularity. And so another question to potentially explore out here is that does imputation help or hurt? And there is a case to be made that perhaps imputation can harm you. And the case goes along the following lines. This is a philosophical argument. So if data is missing, let's say there was a time series and you were trying to count number of steps. And if there is a segment missing, then you are seeking to replace that segment by reconstructing it, right? So the goal of imputation is to fill in so that it's as if the dropout didn't happen. But if you ponder over it, imputation is the hardest inference task, right? Because you're seeking to replace something which was missing to reconstruct it. Reconstruction is always the hardest thing to do, because if I can reconstruct perfectly, then I can always go back and make whatever inference I want. On the other hand, if I'm only interested in computing number of steps in my example, then why bother going through this harder task, possibly doing worse at it, only to take a hit? So there is at least a hand-wavy argument to be made that imputation may not be the right thing to do. So that's another possible question to explore. And a third thing to think about is that data loss can happen because of a variety of reasons. Sometimes it happens because the sensor ran out of battery. Sometimes it may happen because the network outage and there was no buffer on the sending side. But sometimes it happens deliberately. If it's a human type sensing situation, sometimes we deliberately take off the sensor or we shut off the sensory data. Maybe you're going to the restroom, shut it off. That kind of informed missingness is particularly troubling, because if whenever I engage in a particular activity, let's say whenever I smoke, I shut off the sensor, then really your imputation will not be very effective. So informed missingness or deliberate missingness perhaps cannot be imputed very well. Okay, so the notion would be that let's imagine the sensor data was censored away whenever a particular activity was engaged in. And now if I were to ask you to impute, you would have a harder time. So imputation is one possible direction to explore. There are lots of data sets to study, to do these kind of studies with. In the same vein, there is another direction you can explore, and that has to do with augmentation. Anyone knows what augmentation is? Like when we refer in a machine learning process that we do data augmentation, what does that refer to? Okay, so problem that happens is when you collect data, let's say images or sensor data of some form, then they're in the relatively idealized setting. And if you train on it, then your model may work very well on what you train, but not particularly well on things which were somewhat different. So it's very common practice that as part of the training process, we create additional training samples by subjecting the data to the data samples to some kind of perturbation. So like in case of images, in addition to the image we had, maybe we will darken it, lighten it, tilt it, expand it, crop it, those kind of things. And kind of the idea is that by doing this, we are getting a larger data set. So that's a nice thing, right? I mean, larger and yet somewhat different. But also you are exposing your model to the kind of perturbations you'd expect to have in real life. And you can imagine similar kind of things in the time domain. I can like, let's say it's some sort of human speech. We speak at different speeds. So maybe you can time dilate it, time shrink it, maybe you can crop it, you can create some dropouts, you can have some sample rate variation, those kind of things. So we can perturb these things. Now, a paper that came out last week from Facebook AI Research, it shows in context of images that when we do this kind of data augmentation and other similar phenomenon, then it leads to an overall improvement in accuracy, on test accuracy, which is why we do it. But it also results in class-dependent sacrifices, as the paper calls it. In essence, if I have a few classes, my overall performance is improving. On some classes, the performance is improving a lot, but some classes, the performance is degrading a lot. So for example, the paper cites, let's say if you were to use augmentation where you're cropping images. Now, for some classes, maybe the shape is more important. And for some classes, perhaps color is more important. So now when you're cropping the image, classes where shape is important, they will probably take a bigger hit because more information about the shape gets lost. Whereas classes where color was a dominant feature, even if you crop, color is still inferable and therefore performance doesn't take as much of a hit. So ideally, when we are doing augmentation, what you would like is kind of like a concept that in other places is referred to as backward compatibility. You want not only average accuracy to go up, but you want no class to get hurt, right? I mean, it's good if some classes improve. It depends on your notion of what is fair or not, but certainly if one class is improving at the cost of other, that is not good. On the other hand, if everyone is improving, the pie is getting bigger, even if there is some differential performance, maybe still okay because everyone improved. So the notion out here would be to study the same kind of phenomenon, but in context of time series or spatially discrete thing. These guys studied it in context of images and with convolutional network, but it would be interesting to explore the same thing, same phenomenon in case of sensor type time series. A third one, and I've kind of highlighted here what aspect that I'm hoping that I could get to explore. So third one is uncertainty. So uncertainty is a pretty loaded term. When you have a classifier or a neural network, it's very common that they output not simply a class, but they output for each class what's the probability, right? So say 90% is cat, 10% is dog or whatever. 60% person is walking and 10% is running and 30% sitting, something like that. So one could argue that that's captures uncertainty, and a lot of people think of it that way. Unfortunately, it doesn't capture all types of uncertainty. So if you kind of step back and think about what happens in a system like this, there are many sources of uncertainty. So firstly, you may have uncertainty simply because your input coming in has noise in it, has uncertainty in it. Then you can have uncertainty because the object that the sample that you're looking at lies very close to the boundary, the decision boundary, and therefore you may have problems with this ambiguity. It's kind of like, it looks like apple, but an orange. I don't know quite what it is, attributes of both. Then there is a third form of uncertainty, which is, I don't know, I've never seen this thing before. So it's not about ambiguity, but about lack of knowledge, or what is called as epistemic uncertainty. And finally, there is uncertainty that arises when we train. You can take the same training data, you can have the same network architecture, so you're trying to learn the parameters of the same model, and yet you may end up with different models because the random seed that you pick. And studies have shown that the choice of random seed matters ends up affecting things quite a bit. And a very common form of cheating or unethical reporting of results is you run experiments on a bunch of seeds and pick the best seed. That is never right to do. You should always train on 10, 20 different seeds and then do some sort of an averaging on it. But the point being, from the same data, using the same training algorithm, with the same model architecture, you can end up with many different models. And so that's a form of uncertainty, because different people may make different choices of random seed and end up with different models and therefore different results. So all these different forms of uncertainty. So now, one thing that people have been studying lately is, how do we expose uncertainty on the output? How do we get this notion which goes beyond the probabilities of different classes? So there have been some papers in the past few years exploring different forms of uncertainty. They come from a variety of approaches. Some of them think of a neural network or a model not as a single model, but as a family of models. So it's almost like each parameter of the neural network is itself has a distribution over it, and then you try to see what the output would be. So this is uncertainty coming from the model itself. Some people look at, if my input has uncertainty, that is, input is not simply x, but x plus minus delta, then what can I say about the output? What would be the output perturbation? So they propagate uncertainty like this. And a third one is, you seek to model I don't know things. So explicitly. So this is something called evidential deep learning. Okay, so there are a couple of possible project directions out here. One is, much like the first two projects, you can explore some of the different forms of uncertainty that have occurred. And there's a very, as so happens, as in January, there's a nice survey paper that has emerged, which kind of talks about different forms of uncertainty, and also that can be a starting point. Another one, which I thought might be a cool project, would be uncertainty-driven offloading from edge to cloud. So kind of the idea being that smaller models like YOLO 5 or other such things, they come in, like you can have a big version of these models and a small version, more parameters, fewer parameters. And it turns out generally the big models do better generalization, better results, smaller ones not. So what if, instead of, what if we were to use one of these uncertainty measures that have emerged as a way to decide when to consult? So intuitively, the idea being, if I know my own limitations, and when I'm less confident about my results, then I consult an expert. Or in this particular case, the expert would be the bigger model out in the cloud, but using one of the uncertainty-based measures as opposed to simply using softmax, and that would be your kind of baseline. So that's the third direction. And the final one is explainable inferences. So in the recent times, one aspect which has gained a lot of attention is that how do we humans trust, if I'm a decision maker of some form, I'm a doctor or some other person who's kind of relying on the output of a tool, then the tool makes a recommendation, gives an uncertainty, but even then, we are often interested in knowing why the tool is doing this. And the challenge with neural networks is that it's very hard for us to understand why the result is what it is. So there is a set of work which has emerged over the past, again, half a decade plus, which has looked at variety of ways by which a black box model, like a neural network, can attempt to explain to its user why the result is what it is. And a variety of ways this is being done. One approach is we point out to the features. We may say, this is a dog because, and then in the image we can paint, let's say, the mouth of the dog and the ears of the dog, features which were prominent, which make a difference in that decision, which are most salient. Okay, so that's one approach. Another one is you could say it's a dog because I was trained on this image data set, and here is this image which is very similar to this one, and this looks like it was told to me it was a dog, right? So it's by example. So there are these kind of approaches, and it's a very vibrant area of research right now, trying to figure out what constitutes a good explanation. Some people also believe that we should never have black box models to begin with, because taking a black box model and then try to explain why the results are what they are is kind of a lost cause, and that we should use models which are inherently more understandable. So one approach which has emerged in recent times is something called concept bottleneck models. And kind of the idea is that experts may tell you that these features are important when trying to decide the final outcome. Like, let's say it is about some sports. So why is it an out versus your favorite sport? Why is it a hit? Why is a run? Why is a strikeout in baseball or in other games? You can have similar analogs. So there are concepts in which we depend on. So what these systems do is they use neural networks to predict the concepts. So it's almost like there is a layer where the values going across that layer, we humans can understand some semantic behind it, some meaning behind it. And then there is a follow-on network which stitches them together to make the decision. So now the network can say, it is this because this concept was present and this concept was present. Okay. And then the user can go further and say, okay, fine, but what if I flip this concept? If instead of black, this thing was red, how would the decision change? So you can do this kind of causal analysis. You perturb at the level of features and then see what the outcome is. So there's a wide body of work which has happened on explainable inferencing. Almost all of it is for images. Some of it is for natural language text, but that's where kind of largely things end. There is some work which is beginning to emerge for time series data over the past couple of years, but relatively little. So nice little project out here would be to do, if you are interested in doing some project where it's about making inferences from some data, maybe explore how to incorporate uncertainty and explainability into that. Okay, so in time series, you can again, let's say it was time series for ECG data. So if you talk to cardiologists, they always talk in terms of, oh, you have this ECG corresponds to this disease because these are the features which are indicative of it, and they're beginning to highlight that. Is there a way to capture that kind of human understandable features for a task like that? So it could be some medical task, or it could be some I don't know, it could be some sports related task, for example, like what was the quality with which the person hit the ball, stuff like that. So so a couple of ways you could, a bunch of different directions one could go. Explainable inferences over time series, or when you have multiple sensing modalities. Sometimes when the decision is made and there are multiple different types of sensors, you can combine, you can refer to multiple things like For example, I could say, oh, I think this person is from this country because their facial features are like this. And by the way, their accent is like this, right? I mean, there are multiple different things in different modalities I can refer to. Or you can do the same kind of thing with spatial data. So that's explainable direction. There are some additional projects which my students have sort of proposed. So if you want to explore these. So one is, can explanations help select a good model? So this project actually came out of a group at IBM Research. So basically, this is really can guide what model to pick. So the problem statement out here is the following. Ideally, when we select a model, instead of simply focusing on accuracy on your given training set, why not we consider other attributes of the model so that when faced different scenario, so this is the problem of domain shift or across different users, it does better. And one of the hypothesis is that models which are more explainable potentially have better characteristics. So use explainability techniques to identify what features the model was picking up, and then ensuring that those features make some semantic sense, and then picking those models. So kind of, last time I had given this example of a model which learned how to recognize, discriminate animals, but for horses, it looked at the logo of the stable, which was on the bottom right. That would be an example where if the model is giving the logo as an explanation, you filter it away. So notion out here being that could we make use of explanation as a way to guide model selection? If you are interested in this, I can point you to the student. Then there are a couple of projects which are around spoofing detection. So a very common thing nowadays is people create fake audio, fake video, and there is a cat and mouse game going on. There are better and better methods to create realistic fakes, and then there is a fight on identifying such fakes. So this particular slide is about detecting fake audio, but you can imagine a version of it which is about creating fake video. There are a variety of things one can go after. So for example, in case of audio, maybe it is some underlying features of the audio which give away that it was a synthetic. In case of video, there are things like early systems were not very good at like being very capturing like eye blinking very well. So they were a giveaway. Nowadays, things have moved to more subtle ways. So one project idea that I proposed to a group over the weekend was that now that it is possible by looking at the video to get heart rate and breathing rate from the video. And you can get it from the motion, you can get it from the change in color of the skin in the face. And the question that arises is that are these fake videos creating realistic physiological signals also? So if I were to look at a video and it looks like a video of whatever Obama giving a speech or something like that, may look fine in terms of overall characteristics, but if I were to subject it to how the heart rate is or the breathing rate is, would I see some quantities in that? That should be. And the same thing you can imagine with sound. From audio, there is work showing that, like right now when I'm speaking, when I breathe, there is an imprint on the sound. So people have done work like extracting breathing rate from the human speech and all, and there could be other features. So and likewise, a speech which is generated algorithmically may lack in the frequency domain some of the characteristics and noise that are more typical of human thing, right? I mean, coughing and sneezing and stuff like that. So those are the kind of features to look for. So the general thrust out here is detecting fakes. And there are data sets out here, so it's not like if you go around collecting anything, you can work with these. Another one, which is finger writing using IMU data. So the idea out here is that you are wearing some sort of a watch. It has an IMU sensor. Now, people have done the following kind of things. One is detecting gestures like smoking or drinking or stuff like that, macro gestures. Some work people have also done where when you attempt to tap, they try to detect that. People have also done work where you write, like I make a big gesture, O, or write S or stuff like that. What has not happened is when I do fine grained writing. So imagine like you can buy these pens which have accelerometers in it, and when I write it on a surface, it detects the writing because the pen has an accelerometer in it. And now it can detect hopefully small scale writing. But usually, but instead of the pen, what if I were to just write with my finger, like tiny writing? Okay, can I detect that? So finger movement as opposed to the big hand movement. The finger movement trying to decipher what was I writing. Okay, and let's say limiting to kind of a just let's say the English alphabet in numbers or something like that. So air writing, but it is tiny as opposed to like big motion. Now this one does fall into the category of I have data and I'm going to make inferences kind of thing. But the challenge in this one is people vary a lot. So it's not a, so if you were to simply show that, oh, I can train on X users and then just work within those X users, it's not very effective. So in this kind of work, the challenge is how to create a model which is robust to domain shift. That is, when faced with a withheld user or user from the network. So very important in this kind of work not to do the following is not legal, which is I give you data from end users, you take subsets of data from end users, and then you show that on some other data from the same end users, it is working well. What you really need to do is train on some subset k out of end users, do the whole project, and then the remaining n minus k, you are going to evaluate once and only once, and that's it. Ideally, as different as they could be. So anyway, that's a project. If you're interested in, I can help you connect to the student. Another one, cross-device learning. So this is motivated by the following. So we tend to have many devices which are often duplicated. Nowadays, at the very least, we have watches which have sensors and all. We carry a phone. Some people also have like rings and glasses which have sensors in it. So what happens is, as we lead our day-to-day life, sometimes we have all the devices, sometimes we have one device, sometimes we have another device. And the question that arises is that how do we make inferences about human activity when the set of devices keeps changing? When I go out and a job, then maybe I'm just wearing my watch and leave my phone behind. Or maybe I'm going to have the phone, but maybe the phone is tied to the arm, for example. Oftentimes at home, I may have watch on me, but the phone may just be sitting on the charger or on the table. So if you look through your life, it's not like you have all the devices all the time and you have a steady population. You have a very sensing substrate. So the question out here is, how could we have a model which is immune to, or which can gracefully handle this changing sensing substrate? So it's not like, I mean, one approach to do this thing would be say, okay, I have one model trained for my watch, another model trained for my phone, and then I'm always just going to vote on them. Okay, vote after this, I have 2 votes, I have one vote, and then combine it. But a better strategy would be to take that raw data and map it into some feature space, some latent space, and all these it's almost like shared information. That's how our brains work, right? If I see you, I get information about who you are, but then even if my eyes are closed, they're also dark, and you speak, again, it's the same part of my brain, okay, John. Okay, so it's that kind of analogy out there. Could we have a shared representation in the sensors can come and go? So there are various ideas out here. One is how do we learn this kind of a model? So if I have, uh, uh, can I, so you can imagine that I can have a model which takes, let's say there are two devices. Let's take input one and input two. Now, sometimes input one is present, sometimes input one is not present. Likewise, sometimes input one is present, sometimes input two is not present. So what we can also have is one big flag for each device saying present or absent. So now what I have is a mask. It is saying whatever present flag, device present or not, and that's actual data. So and like that for device two, and now can I learn? So it's like a neural network or a model with a multiple branches, and you can now learn something with your presentation. In recent years, again, the people have shown some interesting abilities of these kind of things. There's a group at MIT where they have a school project where they trained a classifier which is for sound and camera. And they show the ability to detect cars. So the idea is during daytime, the camera sees the car going by, so it's very good. At night time, maybe you just have the headlights, so it's very hard to make out the car, but the sound helps it localize. So those are some of the approaches that one can pursue. So this idea behind this project would be to say, unlike MIT one here, the goal would be different types of on-body sensors, but create a model which can gracefully take any data from any subset or possibly all of it. So that would be kind of the goal out here. So anyway, these things are in the slide deck. So if you haven't met me, I know many of you have, or I know all of you are still thinking. No one has finalized the project. So go through it, and I'll try to add the names of the students, but meanwhile, feel free to reach out to me. Any questions before I dive into it? Okay, so again, if you haven't met me, please do sign up for a time slot. I think thus far I have met 8 students or 9 students, something like that. And I know we have 9 students. I'm meeting a couple of more. So I think hopefully I'm meeting everyone in the class. But please, please do. Okay, so last time we were I was going through deep learning, and we had talked about that how to deal with this problem of too many parameters. There were 2 concepts that are used. One is using convolution. So instead of a fully connected layer, we have these convolution filters, and the other one is the concept of pooling. And both of these things have some biological inspiration, but these are meant for I mean, these have been motivated by images for the most part. So if you look at, one of the things that happens is if you look under the hood in a neural network, can you guys, the voice travels in this big room, so sorry, but thanks for being considerate. Okay, so so if you look at specific neurons within the architecture and when they are activated, people have noticed that early stage neurons, earlier layers, get activated by simpler features, and then the higher up, that is deeper into the network, closer to the output layer, they begin to correspond to higher level features. And there is plenty of biological evidence behind this. So I once attended a talk by a famous neurosurgeon here at UCLA called his name is Isaac Fried. He gives fantastic talks. If you ever get a chance, listen to it. So what he does is he works with patients with epilepsy, And what these guys do is they have the ability to put a probe in the brain to examine the firing of a specific neuron. And in case of, so what he has shown is that, so with epilepsy patients, there are some particular advantage in the way their brain gets damaged that they're able to study these things. They find that there are specific neurons which are tied to even concepts like there might be a neuron which fires when you look at, I don't know, let's say John Travolta's face. Okay, so they are that specific, like they get tied to celebrity faces or a particular location or things like that. On the other hand, for let's say less consequential things and all, there may be just a lot of neurons firing, there's a collective firing that's going on. So, so when you look at these things, so when you look at these networks, there is some sort of features that emerge, but philosophically, a question that you must sort of think about is there any reason that the features that the neurons learn carry any meaning to us humans? Now, it turns out that you may see some papers that say, you know, if we look at a particular layer in the neural network, this one corresponded to whatever obese people, this thing corresponded to tall people, this thing corresponded to fair people and all. But there is no rhyme or reason or evidence that it has to be necessarily the case. So, so there are papers kind of making the case. Also, what you do see though is that the spatial scope of what a neuron covers grows bigger and bigger. And if you were dealing with time, it would be the same thing, that the earlier features are basically filters acting on small intervals of time, and the later ones are filters acting on bigger period of time. They're like mashed filters detecting some particular patterns. So anyway, so the whole concept of convolutional network together with pooling became a powerful vehicle to have much more memory efficient networks than a fully connected network. But a lot of problems still remain. How can we handle temporal sequences? Okay, the whole thing emerged out of images, and it kind of how would we handle temporal stuff was unclear. How can we handle sensors that are distributed irregularly? Okay, so images are insanely regular. If you think of each pixel as a sensor, essentially what you have is an array of sensors. Now, some other places you encounter these kind of sensors, right? Sometimes radio have antenna array, very regular. I may even deploy sensors in space regularly, but that would be kind of rare. So more generally, we have irregular sampling often. Even in time, we have irregular sampling. Like, for example, every time you go to the doctor, they take your vitals, but the time series of those vital signs is not regular because we don't go to doctor on a fixed frequency basis. How do we handle multiple sensors of different modalities? That question, now, you could say images is multiple modalities because it has sensors tuned to 3 different wavelengths, RGB. But more generally, modalities can differ considerably. How do I combine data from an array of microphones with data from an array of visual sensors? Sometimes even sensors in the different part of the spectrum may have different resolutions. Like I may have a RGB array, but then I may also have a terahertz thing which may only have a few thousand pixels. So modalities, how can we handle missing data, bad data, misaligned data? So these are all questions which your basic convolutional network paradigm doesn't adequately answer. You have to clearly have some stuff around it, and so we'll look at these things. So the topic now is what kind of architectures have emerged for deep learning over temporal sequences. So the basic simplest version of the problem is I have a time series and I want to classify it. So a univariate time series, where just basically you can think of as a vector of some real number values. And it's assumed that these values came from some sort of a sampling regularly in time, but at the level that we are dealing with, what we have is a vector or a sequence where we have a bunch of samples. And so there's no explicit notion of time, but the only thing that matters is order. So it could be text or it could be some uniformly sampled notion of time. So that's what we start out with. I have a time series, x1, x2 through xt. The part which is important is there is an ordering out here. I can't just shuffle it. If I shuffle it, I don't expect the result to be the same. If I have an m-dimensional time series, then each one of these inputs, x1, x2, x3, it is it itself is a vector. So so I would so you can think of it as every time step I'm getting a multi-dimensional vector, and I have a bunch of them. So the task out here is the following: that I'm given sort of these sequences, and I'm given corresponding label. So each x is either scale time series of scalars or a sequence of scalars, or it's a sequence of multidimensional vectors, and then the whole thing is a label. So kind of typically setting often is that I may take, let's say, some duration of vital signs of a person, and then I'm seeking to detect whether they have a particular disease or not, for example. And then kind of the idea is that much like our usual classification, the value of y, which corresponds to our class, is what is going to be 1. So in that sense, it's pretty straightforward. Now, common PSC task looks like this then, that I have a whole bunch of okay. So I'm given time series of some length, and then I have kind of as input some sort of a multivariate time series. It could be, let's take ECG. So ECG often is done with multiple electrodes. So you have single lead ECG, but you have oftentimes ECG with as many as 12 leads. So essentially, your input is some time series, which has, in my example, 12 dimensions, and then has certain duration. And now you're seeking to classify that. So issues that come up out here, in simple version, we kind of assume our input, our training sample, everything is of the same duration. But in general, that is not the case. So what if time series are of different durations? So that could be one thing. Like one patient may have give you a week worth of data, another patient may give you a month worth of data. What do? Do you always just go back to the shortest, or can you make use of more data? What if time series is long so that the labels change? So if it's an activity one, if time series is very long, there may be multiple labels that may occur during that period. So activity recognition is like that. So a very common approach, as something that I alluded earlier also, was that we divide these time series into windows, and then we do a recognition within each window. So we chop it up into some window size, and then apply some sort of a temporal deep learning architecture to make the decision. So application to sensing tasks. So just like in this domain of HAR, human activity recognition, what people do is they look at sensor data collected from different parts of the human body, or maybe in the surrounding space, and then sort of recognize activities from it. Likewise, sound is another very common modality where people try to perform these kind of tasks. Going back to her, then the kind of questions that people seek to examine are trying, like the reason human activity recognition is done is sometimes it correlates with our health, sometimes it's part of human computer interaction type interfaces, sometimes, excuse me, may I request you not to please, it's very distracting if you for listening, so thank you. You're welcome to join via Zoom, if you wish. Okay, so the objective can be manifold. A very common sensor in this case is IMU sensors, as I mentioned, mostly because it's a mature technology. It's built into so many of our devices, even to the extent that now you can buy like battery operated rings. There's a company called Aura, for example, OURA. They sell these rings, which a lot of people are very fond of, and they can collect all sort of like sensory data. Some of our earables have these things. So if you have a AirPod or one of these kind of things, they have inertial sensors. There are companies which have eyeglasses with inertial sensors built in. So at the very least, ear, eyeglasses, rings, wrist, and of course your pocket or purse. These are some examples. Then there are some other more specialized ones like shoe inserts, or also there are Nike makes one. So there are lots of ways that one can collect the sensor data, but the easiest one is watch and phone. So the standard approach, as I alluded to in a prior lecture also, is that we collect such data, we divide them into windows, oftentimes sliding windows as opposed to sort of independent windows. We do some feature engineering and we do some pattern recognition. But what deep learning methods do is very commonly, or at least a simpler version is that we take these windows of time sequences and then we subject them to one of the temporal deep neural network architecture. And I'll talk about them a little bit later. Audio analysis, similar approach. There are one area why audio stuff is useful is just as a recognition thing, but also there is a whole rich field of audio event analysis. So there's work which tries to infer activity from acoustics, location from acoustics, like type of location. The background sound can tell are you in a restaurant or shopping mall or stuff like that. So audio analysis, audio activity is another one. So how do people deal with time series data in the deep learning world? So again, kind of classical approaches, like I said, divide into window. Within the window, you do some feature vector, and then you train a classifier, and you're done with it. So how do we do with time series in the deep learning world? So the first approach that you may think of, is, I know how to do images very well. Perhaps I can convert my problem to an image problem. And that can often work in some applications, in many applications quite well. So how can we convert time series into images? Well, one way you might think of is that I convert it into a spectrogram. So I take over time windows. Basically, I'm doing a short time Fourier transform. So I'm sure you have seen these kind of spectrogram pictures. And looking at these, oftentimes patterns become very discernible. Lots of things have very dominant frequency components, and when viewed in this way, they become very visible. So there's a body of work out there which takes time series, does short time Fourier transform, converts them into a spectrogram like this, and then much like we human experts look at these and can say, oh yeah, there is a peak out here and that's not what I expect and all. You could imagine that neural network can do kind of the same thing. That's one. Another way of converting time series of certain types, maybe when you are doing spatial analysis. So this is movement trajectory in 2D. And looking at this trajectory, oftentimes you can make a lot of inferences. For example, how much did I move? You can begin to get behaviors. If there are multiple people, you can begin to get some additional information. So this approach of using trajectories embedded in 2D space or 3D space to then analyze things using standard vision-based neural networks is very common for at least macro movement analysis, right? I mean, if you look at a map and all. What do you think is the drawback of these kind of approaches? Let's take this right one. If I take GPS location space and I embed it into this kind of a 2D diagram, what am I losing? Anyone? Come on, guys. Yeah, please. Yeah, so we are losing the time information, right? I mean, so what's happening is I get to see where I go, but I don't see, at least in this way, the rate of movement at any given point in time. It could very well be that I was in this point and I spent an hour there. That information is just not coming out. So this approach captures obviously some type of information, but it's also losing some information. What about this guy? This sort of short time Fourier transform type approach. So again, this one at some level is capturing all the information, at least subject to whatever is the temporal granularity. So this one is hopefully better. And again, these are just two exemplars. There are other approaches that also exist. So spectrogram, basically, you have time and frequency dimension, and then you are working this. Unlike pictures, the problem with spectrograms is that they have non-local relationships, in the sense that there may be, because we are dealing with a time dimension, if there is things which are occurring in a periodic basis in time, then they will manifest in the picture as some sort of a periodicity over time, in the sense in the X dimension. And so this assumption that we have with regular natural images, that convolution, local things, that's not really present out here, strictly speaking, right? I mean, there is no reason that that we are here. We are interested in connections which exist at a longer time distance, but hopefully the idea is deeper layers can potentially kind of capture it. So one has to be careful in this one. Trajectories in 2D space. The challenge out here is that if you look at this picture out here, it's a very edgy picture, right? Lots of edges and all, and that's not what CNNs are really good at. So CNNs don't work very well when you are primarily edge type stuff and not textures. But nevertheless, people try it. Time dimension, as we discussed, is lost. And then, of course, if I have sensory data which is more than two-dimensional in nature, then it would be hard to embed. So one of the area that people have explored is, are there image-like representations which can work with multi-dimensional data? Okay, so kind of the idea is, can I take a multi-dimensional time series and then somehow embed it into an image-like structure to do it. So again, spectrogram works with unidimensional, movement trajectory works with two-dimensional, but what is there a general story that we can do? So in the literature, there are some methods that have emerged that people explored. There is one which is the notion of recurrence plot, and let's see, and then another one called Gramian angular fields. So what these things try to do is they try to map the time series into some sort of a phase space, and they try to look for patterns there, and then they map those patterns into the 2D images. So what is happening out here is they are looking for trajectories in that multi-dimensional space and then projecting those trajectories back into this 2D space, which is what they call as recurrence plots. The nice thing out here is that they are very good at capturing longer term time patterns that may occur, regularities that may occur in time series and all. So that's one, that's recurrence plot. These are some examples of like how different time series end up looking at different images, and then you run the CNN on the image side. So that's one. This Gramian angular field is another approach. Again, it goes through kind of some elaborate framework, but the idea eventually again is that we map the time series data into images, and then the patterns in these images capture the recurrence, the temporal patterns that exist in the original in the original time series. So, and the third one is Markov transition field. I'm going to skip these, but point is that's kind of the lazy approach, or people tried it because they said we know how to do computer vision very well. Let's translate time series into a vision problem, and then just apply the vision problem. In some domains, may make sense, like if you know that spectral features are very important, then maybe the spectrogram approach would be a reasonable one. But it would be better if we could directly have deal with the time series data directly, natively, as opposed to kind of just going to this image domain. So that leads to the second approach, basically directly adapting neural networks to work with time series. So one approach is to stick with CNN, except work with one-dimensional features, and that's kind of the obvious approach one could think about doing. So, for example, let's say you were receiving three channels of sensory data. So what I could do is I can take each sensor dimension, and think of it as a one-dimensional image, and then go through a one-dimensional convolution like pooling pipeline, and then combine their results into a single layer. So so your convolution is now going to be instead of k by k would be 1 by k. All the other things apply. It makes sense logically at some level, because the same reason why we had convolution in images, namely nearby things are important, and that there is stationarity kind of hold true for the single dimension time series. So we are doing the same thing. So you apply independently convolution max pooling on each dimension, and then kind of combine it together. Now, in reality, for many sensors, there is correlation among these sensors. And so a challenge that you do face out here is that the first time you are combining, you're looking at the correlation across these things is when you're combining at this layer. So in the challenge with this kind of architecture is that early stages of feature extraction, you are operating independently, and maybe it would benefit to have some early information exchange going on out there. So there are some architectures where there's some early exchange of information happens, but a simple architecture would be, yes, I treat each sensor as an independent image, except a one-dimensional image, and then I take the evidence from each one of these and combine it into a hidden layer. So that's a simple approach, but you can imagine other alternative ways of combining these things. So one approach is this, where I take, let's say I have three sensors, I take three sensor data, I now think of it as an image, which is a 3 by k image. So in a sense, I think of the vertical dimension out here, the three sensors, as kind of a dimension of the image. This one is what I showed in the previous slide, and there are variants of it. Now, do you think, like, what do you think are the trade-offs between these two approaches? Thinking of each sensor data as independent 1D images whose results I combine in a hidden layer, versus thinking of my K sensors, my D sensor dimensions as like one of the image dimension. So like I have D rows or 3 rows out here, and then window corresponds to the length of the row. So I think of an image, and then I apply my standard 2D processing. Do you see any issues or logical problems with the left one? Like what's can I truly think of it like an image like this? I guess that's my question. And if not, why not? I guess I'm leaning to obviously nudging you towards like, yeah, there is a logical inconsistency out here. What do you think might be the problem here in terms of thinking of the stack of sensors as kind of rows of an image? So think about like a regular image. If I were to shuffle its rows, it makes no sense, right? I mean, if I shuffle the rows, then I don't expect the image to be classified the same way, right? I mean, it no longer has the same meaning. On the other hand, if I shuffle my sensors, I do expect the results to remain the same, right? So thinking of multiple dimensions of sensors in this manner is a risky proposition, because you are imposing an unnecessary ordering over it, where in image that ordering is needed, and that is why we have convolution, that nearby things are related to each other. But in case of sensors, what we want to make sure is that in the sensor dimension, if I were to just call, if I were to shuffle these things, there is no rhyme or reason anything changes, right? So so one has to be very careful out here when applying 2D convolution. I think this is perhaps more appropriate architecture generally, but these are some of the approaches that are done. So CNN can be used. A challenge with CNN is that we have to design a network with certain input size in mind, right? I mean, like our image neural networks are designed for certain size image, like whatever, 32 by 32 images. Likewise, this stuff will need to be designed with certain time series length and time in mind. So maybe it will take 32 sample long sequences. Challenge with this is that what if the sequence length changes and all, what do we work with that? Another one is there's no way in this case we can take into account history of some form. Like, for example, if I want to capture that I have a window and I'm making a decision, but I want to incorporate information from another window. There's no memory in these architectures within within the neural network. Whereas when we think of time series, that's probably a logical expectation that there should be some way of capturing memory, much like we were doing with dynamic Bayesian network and HMMs in the classical methods. So that leads to the third approach, which is recurrent neural networks. So recurrent neural networks are also pretty old. So CNNs came in late 80s, early 90s. Recurrent neural networks are also somewhere around the same era. So these are again, when we kind of talk about these, often you think, oh, all of these are pretty recent, but it's actually decades old. So recurrent neural network is to Convolutional neural network, kind of in the sense that you can think of former is memoryless, this one has memory. You can think in digital system terms, the former is like combinational logic, and this is like sequential logic. Or you can think in signal processing terms that convolutional networks are like finite impulse response filters, and these things are like IIR, infinite impulse response filters. So essentially, these are systems with memory, and let's see how they work. So the idea is that these are neural networks which are designed to take sequences and then make inferences on it. So, so what we saw previously, thus far with CNN, you can think of it that CNN takes one input and produces one output. But in many cases, you are interested in sequences, and there are a few possible things you can imagine. One is, given one input, I potentially want a sequence as an output. So for example, I can give an image, and I may ask for a caption describing it. Or in context of sensors, it could be I can give a image of a person doing something, and then I can ask for, in a time window, what the accelerometer clip might look like. More important for us for activity recognition is I give you a sequence of sensor samples, and I want a label out of it. I want some many to one, right? I'm classifying or doing some regression. So it could be like I show you something and I say how many steps did the person take, or was he running, or estimate the speed, those kind of things. A single number. Sometimes we are also interested in many to many, and in this case, we are converting one sequence to another sequence. So the common example is given from speech and natural language, which is I may be saying something in English and I want it in a different language. So with some delay. And oftentimes immediately, right? I'm giving you something, and without any delay, I'm kind of wanting output. Now, in the sensory world, this thing is often referred to as sensory substitution. Kind of the idea being, I'm giving you one type of sensing modality, and I want you to translate it into a different sensing modality. To give you an example, something I'd read where in robotic surgery, they want to convert image or video from the camera at the end of a catheter into force feedback for the surgeon. So then the surgeon gets the feel as if they're operating with the real tissue. So that is an example of sequence to sequence conversion, the video being converted into a force feedback, a haptic feedback directly. So, or another example, which I was giving earlier, which is you have a video, silent video of lips moving, and you want to generate the sound from it. So that would be an example of sequence to sequence. Or another one, kind of a paper which I saw last year out of Georgia Tech. And what these guys were doing was there was a video, and then they would place a virtual accelerometer on some body part. So like, let's say there's a video of a person walking around, they would put a virtual sensor on, let's say, the arm, and then the output would be what the accelerometer reading of that virtual sensor placed on the arm would look like. So models for doing these kind of things, they will all fall into this category of I'm taking a time series sequence and I'm generating a time series sequence. So all of these are useful, while the common examples of these things come from usually from natural language, but they are present in time series also. By the way, these are some of these things. Applications could also be kind of cool project ideas. So how do we process these things? So for this stuff to happen, we have to introduce the concept of memory. If you go back to your digital system courses, where the difference between combinational and sequential was that there was memory, right? There was a state register in which from one time step to another time step, we maintain some compact representation of the history. So same thing out here that happens. So these recurrent neural networks or RNNs, what happens is that at every step, we take the input and we take the state vector and we produce the next state and we produce the output, much like any sequential logic does. So, so you can think of it like a program which has a local storage in which storing the state. I like to think in terms of sequential system, like I said, the state register, and then so CNN viewed in this way have no state, so they only have current input and current output. Every time step, they take the current input, compute a function of it, and output the current output. Whereas RNN at every time step take the current input and the previous state, and they produce the new state and the current output. So, so that's happening. And this general view can hold true whether your inputs are vectors or scalars or whatnot. So you can apply this thing even to images. As you might imagine, that instead of like oftentimes for many things we kind of scan the image. So as we are scanning the image, we look at one part, and then when we process the next part, we carry information over from the previous part. So even for something like images, you can imagine this concept of processing in sequence is useful. For time series, it's very natural, right? So if I'm looking at a video, a frame that I look at, I analyze it, taking into account the frames that came previously. If it is accelerometer or speech, same story. So recurrent neural network have that. So you can think of RNNs as then CNN plus memory. Memory, in case of images, it is memory over space, but for us, it is memory over time. So memory from the previous time step. So the new state, h of t, is some function of the previous state, h of t minus 1, and the current time input x of t. And this function is what whose parameters we are going to have to learn. So you can think of RNN in this term now, said that it has xt, it's giving yt, and there is a local feedback. At every time step, we are producing h of t, which is being used also. So in some senses now, the RNN has two functions in it. There is the next state function and the output function. Again, if you go back to your digital systems, we think of sequential systems as having two functions in it, right? The next state logic and the output logic. Same thing out here. That RNN really you can think of as these two pieces. One piece which computes the next state, and another piece which computes the y of t. So that's kind of the idea. You need to specify, and before that you need to learn these two neural networks. Again, that's the general framework of RNN. Now, question then becomes, how do we, just like in case of CNN, we kind of created the structure, right? Instead of arbitrary, fully connected things, we thought of a particular architecture to structure them. Same thing with RNNs, that there are specific architectures that became popular for RNN, but the general RNN framework basically is one where you have next state function and an output function, and they could be anything. So now the question becomes, how do we learn the parameters out here? So deep down, what you really have is, like I said, just a function which is sort of computing the next state, and a function which is computing the output. So this green blob is our, sorry, this f of w is our function. It takes the previous state, produces the next state, and then at any given point in time, there is a separate function which is computing this y of t. I need to learn parameters of this function fw. My training in this case is I'm given a sample, sequence of samples. So these are the x's, and I'm given a potentially in general a sequence of output. So my training now, instead of happening over an image and a label or a feature vector and a label, is really over this time sequence producing another time sequence. So the way to think about it is that I can unfold things in time. That is, if you start from the final time instant, you can go back in time, and every time step, we are doing this operation, taking the preceding state and the current input and producing the next state and the corresponding output. The challenge that you face in this context is that I want to make sure that the weights that I'm using for FW in every time step is a common set of weights, the same FW, because we are unfolding in time. So this is a little bit, you can think of it analogous to our CNN, the filters we were using in CNN, because we were applying the filter at different points in space and over the image, but they had a common set of weights. Here, FW is applied at different time steps, but it's the same FW. But the challenge out here is that you have to go potentially all the way back to time step 0. So this overall time duration can be pretty long, generally speaking. If I have a long sequence, then I may have to go all the way back to the start of the sequence. But that's kind of basic idea, that we are going to unfold the neural network in time, and then we are going to learn parameters over this, much like we learned parameters for a general neural network. So this unfolding in time is a very key part of RNNs. So the way the learning proceeds now is, you are given a sequence, you are given a desired output sequence, and of course what you're predicting, you compute the loss function, you do the backward propagation, except backward propagation is now happening over time, and that can lead to a lot of problems if you have an arbitrary amount of time. If you have a running system, then to compute the impact of error at a time step, you have to go all the way back to t equal to 0. So so this state, I mean, conceptually, the state is being carried forever. The state has infinite memory, potentially, right? Because if the system has been running for a year, then the state vector there represents memory of all the inputs that were encountered. In reality, memory is memory decays, right? I mean, so some of the papers suggest that these kind of architectures, like in case of a video, for example, the memories that they have are a few, like 10-15 seconds. They don't depend upon things way in the past. Much like us, I mean, we kind of give more importance to the recent memory than the past memory. But it's all a matter of time scale also. So when I said 10-15 seconds, depends on how you are sampling it also. So given that way old memory doesn't matter, usually in this back propagation, we truncate the time. So we kind of go up to some distance in the past and only look at that. So unlike the idealized picture where you kind of go all the way back to the past, we truncate. There is another realistic reason to do it is, as you go way into the past, then there is very little impact, and there's a problem called vanishing gradients that you run into. So numerically, the whole thing becomes unstable also. So long story short, we unfold the network in time for some window, and then we compute the error over that, and we estimate the parameters over that truncated time window, and we keep doing that process again. So at every time step, we look at a window, we compute the error over that window, and then update the parameters based upon that. So that's the high level picture. The question then becomes, what is this green box? is this green box an arbitrary, fully connected neural network, or does it have some structure behind it? And that is where different RNN architectures have sort of taken different paths. So two which emerged as widely used. There's something called long short-term memory, or LSTM. I'm sure you have heard of this. LSTM came out in 1990s. And then there is something called GRUs, gated recurrent units. This came out of Stanford, like 2012, 2013 timeframe. So it's much more recent. There was a bit of a spat over this one. When GRUs came out, they didn't even cite the LSTM paper. So there was a bit of a bad blood between them, but eventually they fixed that. Now, what is happening out here is the following. There is a particular information flow that they have put out here, and they call it LSTM, long short-term memory, because they created this architecture somewhat loosely inspired by what they claim is how human brains work. That we have long-term memory, we have short-term memory, and there is sort of learning takes place at different time scales and all. So the architecture out here, the original paper, had some loose inspiration in terms in terms of that. And what you see out here is the kind of functions that you usually have in neural networks. Okay, so these there are sort of fully connected elements, there are gates, there is some other operations happening, but this is kind of capturing, is their attempt to capture kind of the flow as memory is built up. And there are within this thing, they're getting stuff from the previous stage. So the state itself is now divided into kind of two parts. There is the C of t minus 1 and h of t minus 1, and then the next state is C of t and h of t. And the GRUs, their claim to fame was that it is simpler than LSTM, but I think at the end of the day, LSTM is the one which more people sort of continue to use when they use this. So the green box looks like this. Again, LSTM and GRU are widely used, so they are kind of built in. These things are readily available units in any sort of decent neural network framework. So, so the appeal of these kind of systems, LSTM, GRU, is that in principle they can capture memory. In principle, you could argue if I throw at them long-term time series and all, they should be able to learn long-range dependencies if possible. So, so for example, I show them a video. Let's say we are capturing long-term videos from a camera installed someplace. In theory, at, given enough data, enough labeled data, they should be able to answer, because the state is capturing information about the past. The issue is, in reality, so while in principle the state captures information infinite into the past, in reality, as I mentioned, their ability to capture history is more limiting. So, so in a lot of applications, it is sufficient to look at the recent history, and I think much of the state of affairs in this field is those kind of applications. So no one seriously applies LSTM where you're trying to connect the dots between things which happened weeks and months or years apart, or even hours apart. Usually, these systems are used for things which are short time scale, like looking at a window to figure out, am I running, walking, stuff like that, as opposed to a longer term event like did I do something since I arrived at UCLA? Okay, so those kind of questions, I think too much memory for these things to effectively handle. So they excel where some limited context is enough to help you. But if on the other hand, long context is needed, then these systems are not very good. So there are some, I think these are kind of made up examples, but let's say I have cameras in a hospital and I want to detect whenever a nurse sees a patient, doesn't wash the hands, and goes and sees another patient. And these things can potentially be minutes or tens of minutes or even scales of hours apart, right? Those things are very hard for LSTM to detect because the memory, that degree of memory, contextual memory, they don't make it. On the other hand, they're very good at detecting short time scale things like short video clip, may have what activity I'm doing, let's say chopping onion, and detect that, while or things like a bowler bowled and the batter hit, it can detect those kind of things. So short, like seconds of clips and all, they're very good at, but long-term events, reasoning about them or working with them is pretty hard. So, but there are applications where we need more context, where we need to work with not just the immediate but longer term sequences, and therefore one needs to go beyond sort of RNNs there. So RNNs don't do very well in those contexts. So I would say again, there is a term which is sort of often they use, complex activity recognition or complex event detection. So these often refer to things where you're examining long-term things. So another example would be, let's say you have sensor in the kitchen and individual activities like I'm washing vegetables, or I open the fridge, or I'm cooking on the oven. These things RNN can detect very well, individual activities, but stitching these simple activities into a complex activity like was I cooking or was I cleaning up after cooking? Those kind of things where you begin to examine things over a longer time scale, there you kind of begin to run into problems with these systems. So the more complex activities are harder to work with. So when you think about long short-term memory, the long here is not long as in arbitrary long. There's still finite time scale. So in fact, one area again for projects would be interesting to examine that these different approaches for working with time series type data or video data, what kinds of activities over what time duration is the current state of the art, how much can they push, is it simply a matter of not having enough label data, or is it something fundamental about these systems that prevents them from working with long time scales. So LSTM is the most popular of RNNs, and like I said, it was designed to learn long time scale dependencies, but again, the long still is not long in the sense of arbitrarily long, but longer than what you might like tens of seconds kind of things. So the core idea behind LSTM is that they have two types of state information that is being passed through, and then these little bubbles out here, they essentially add or subtract to the information. So they kind of try to model it after, like I said, loosely the processes in the human brain. So there is addition or deletion of the information, which in turn is covered by kind of gates that they have to do this, and that is how the state is being computed. Okay, I'm going to skip this. So there are many variants of LSTM. Most common one is the GRU that I mentioned, and it again has these, it's loosely inspired. So both these architectures have the concept of learning new things and forgetting things. So whenever we have temporal stuff, there are basically two decisions you have to make. This new input that you are getting, based upon that, what new information you should add to the state and what should you forget. And then you should also think of that state as having multiple time scales. Some information is long term, some information is short term. So these architectures seek to sort of attempt to mimic that process. Very well understood at this point, in the sense that widely adopted. Why they work precisely and all is less clear. Most of the time they're just used as black boxes. Now, in reality, what happens is that you combine these LSTM or GRU architectures with convolution in order to create what are called as conv LSTM systems. And they are probably, in general, that's the architecture you would use. So what happens now is, if I go back, I kind of gave the impression as if the inputs to LSTM were your raw sensory inputs. But that is not how we work with them. So what typically happens in these systems is, that we take our sensor data, we go through our CNN layers and all to come up with some sort of a vector representation. So essentially a vector of features. And then we do LSTM over those. So the one way of thinking about it is, in classical CNNs, we do the pooling and then we feed it through a dense layer, which is a fully connected layer. And then we do softmax. In conv LSTM, that layer is replaced by LSTM. So essentially, at every time step, let's say you are getting an image frame or a bunch of sensor data, you use convolution to map it into a vector, and then you apply LSTM or perhaps even multiple LSTM. So the output of one LSTM feeds into a next layer LSTM, which is operating at a higher, coarser time scale, and then eventually you do a softmax over it. So a very popular architecture for processing sensory data then are these kind of architectures. Raw sensor data, convolution to extract features, LSTM to capture the time, and then you feed that output to a softmax layer to get your classification. So starting a few years ago, kind of for many sensing modalities, that kind of architecture emerged where convolution gets combined to LSTM. Another change which has begun to happen in recent time is people have observed that a lot of sensory information is about phenomenon where frequency is extremely important. And therefore, there's a class of networks which have emerged where before, instead of doing convolution and pooling, we basically put layers which are designed to do short time Fourier transform. And then we do the same. The rest of the stuff remains the same. So in effect, kind of the notion being that a lot of phenomenon deep down are being triggered by some oscillators. Like even when you walk, your body has oscillatory behavior. And so kind of the theory goes that instead of convolution, perhaps frequency is the more dominant thing to go for. So several groups have pushed for those architectures. So conv LSTM is the one which is very popular among sensory data. And then, like I said, one can stack these LSTMs so that you can begin to deal with things at different scales. So kind of the idea being that at a fine time scale, you may be examining micro motions like I'm taking steps. At a longer time scale, you will look at behaviors which are over longer time duration, like I was walking, then I was sitting, then I was doing something else. So this notion of stacking RNNs or stacking LSTM becomes important. So in some senses, output of one LSTM layer is input to another LSTM layer, another RNN layer. So architecturally, now they look like kind of stacked things. So let's see how are we doing in time. Okay, these two. So RNN RNNs are widely used in this manner, but one I would also say that in recent times a new type of model, which we'll talk next time, has begun to emerge, called transformer-based models, and it's a move back towards CNN. So there are these two camps: one which say we can do everything within the CNN world by having this new addition called transformer, and the other one is that no, we want to explicitly model time, and recurrence neural network and LSTMs are important. Now, RNN, once you have learned it, you can think of them as a model for the sequence, right? So you can think of them as they are learning the distribution between the input and the output sequence, and therefore you could use them also in a generative mode. You can use them to generate sequences and not simply classify sequences. So that's the other use of RNNs as generative thing. You can, another way of thinking about RNNs is a little bit like our the classical model, like the hidden Markov model or the dynamic Bayesian network. Okay, they can be used to classify, but they can also be used to generate. So RNNs went through. Firstly, they are still used very heavily, but they were particularly before the so-called transformer models emerged. They were very popular for any sort of sequencing task. So now going back to this HAR, the human activity recognition, there are a variety of DNN models that exist, right? So you can start with the simplest. I have sensor data. I look at a window. I can use CNN to kind of classify it. I can do LSTM type networks. I can do hybrid networks. So, faced with sensory data, there are a variety of ways to approach it. Most of the results seem to suggest that these kind of hybrid convolution LSTM do pretty well. And so some version of that would be a reasonable way to approach these things. So this is an example where for some particular hard task, we have a MLP, multi-layer perceptron, so essentially everything fully connected. We have a CNN, we have an LSTM, and we have a convolution CNN convolution with LSTM. And in this particular case, you see that this one does much better than the other. So reasonable sort of choice to have. Having said that, there are, in addition to these metrics of accuracy and S1 score, there are a lot of other things that one has to consider, cost and robustness and things like that. But I think starting a few years ago, like 2017, 2018, those kind of time frame, generally these architectures, convolution LSTM became kind of the one that people started preferring. Same thing with, I think I'm going to, okay. So similar thing happened with acoustic. So there were, again, a body of work around that as well. I'm going to stop out here. Next time we are going to look at the next set of models that emerge, which are these transformer models, and which I'm sure if you've done vision and NLP based thing, you may have heard about them. They're kind of the rage in that discipline, and they have begun to emerge also for sensory data. So people are using those sort of models here as well. But wider practice, these convolution LSTM models are the ones which are preferable. Okay, so I'm going to stop out here. Again, if you haven't set up a time to meet me, please do. The newer projects that I listed, they are part of that file now. set up a time. Evenings work well. And those of you already met me, try to take within the week. So that would be great.